Hello. In the previous video, we discussed the implementation of field-oriented control for BLDC motors with a focus on current control. It was shown that the controller parameters, such as KP, KI, KD, as well as the accuracy of encoder calibration, play a crucial role in determining the motor's performance and stability. Hard-coding these parameters is certainly inefficient. To simplify the tuning process, we need an interface that acts as a bridge between the user and the controller. Imagine being able to change parameter values in real time without having to reflash the program. However, the next challenge is volatility. Every time the device is powered off, all the tuned parameters will be lost and revert to their default values. This becomes a critical issue, especially for encoder calibration. Should we really have to recalibrate every time the system is restarted? Of course not. Therefore, in this video, we will cover two fundamental solutions. How to create a USB communication interface for modifying parameters and strategies for saving those parameters into non-volatile memory. On the hardware I've built, I've already prepared a USB Type-C connector that is directly connected to the USB full-speed port of the STM32 F405 microcontroller. The physical connection is ready. But in order for the computer to recognize this board as something other than an unknown device, we need to program it to function as a USB CDC, also known as a virtual COM port. To do this, in STM32 CubeMX, enable USB OTGFS in device-only mode. Then, configure the USB device under middleware and software packs as a communication device class or virtual COM port. CubeMX will automatically generate template code and integrate all the middleware required for USB CDC. However, the template provided by CubeMX only supplies the driver, not the application itself. We still need to implement the callback function to handle data received from the computer, create a parser for our own commands, and design a simple communication protocol so that the microcontroller and the software on the computer can understand each other. One very important aspect in analyzing the performance of control system is the ability to visualize data in real time, similar to what a serial plotter does. Indeed, there are many open source tools, such as the serial plotter in the Arduino IDE, that can be used for this. However, most of them use string or text-based communication protocols. String-based protocols have a drawback. For example, 3.14159 must be converted into a sequence of characters, which can take up 7 bytes. The more digits and data channels that are transmitted, the more bandwidth is consumed and the slower the data update rate becomes. To overcome this limitation, I developed a simple software based on .NET. The concept is to transmit data in 4 bytes binary format according to the IEEE 754 float standard. With this approach, each value only requires 4 bytes. This makes the data transmission process much faster and more efficient, while the displayed values retain exactly the same precision as those in a microcontroller. In this software, the plot's title and legends can also be modified by sending specific protocols. To make this plotting software truly flexible, I designed a lightweight and efficient custom communication protocol. This protocol allows the software to distinguish between different types of commands or data being sent, rather than just receiving numbers. In essence, I use a 2 bytes header as an identifier for each type of data packet. If the data being sent is for plotting, the first 2 bytes are 0x558A, followed by a sequence of 4-byte float data to be displayed. If multiple channels are present, the data is simply arranged sequentially. This data packet ends with a 2 bytes footer 0xAA55. To change the graph title, the first 2 bytes sent are 0x0400, followed directly by the string containing the new graph title. To change a legend name, the first byte sent is 0x03, and the second byte specifies the index of a legend to be changed. This header is then followed by the string for the new legend name. In addition to the fast plotting feature, I also equipped this software with a command line interface or CLI. Through the CLI, we can interact bidirectionally with a microcontroller. Not only can we receive data for plotting, but we can also send commands to perform parameter tuning, such as changing the values of KP, KI, KD, switching motor control modes, and various other functions. The core of this CLI is that we define a specific command to perform a certain task. Then in the USB CDC receive callback, we parse the command so it can execute the corresponding instruction. For example, mode equals 1 to switch into speed control mode, SP equals 10 to set the motor set point to 10 RPM, KP equals 0.1 to set the KP value to 0.1, and so on. Once we can easily adjust parameters via USB, the next challenge is, how do we store them permanently? The tuned parameters that we work hard to obtain must not simply disappear when the power is turned off. The most common and reliable solution in embedded systems is to store them in flash memory. On the STM32 F405 microcontroller we are using, there is 1 MB of flash available. This capacity is far greater than what is usually needed by our program code. The flash memory for the main application typically occupies the initial sectors, starting from sector 0. Therefore, the safest strategy is to use the last sectors to store the parameters. This minimizes the risk of overwriting the running program code. I grouped all the parameters that need to be stored into a C struct. This makes it easier to manage the data as a neat single unit. Writing to flash cannot be done arbitrarily. The process must begin with unlocking the flash, then erasing the targeted sector, writing our struct data byte by byte, and finally locking the flash again to prevent unintended writes. When the system is powered on or reset, the first step is to read the data block from the last sector of flash and copy it into the struct in RAM. This way, all parameters immediately retain the same values as before power was removed. However, there is one critical problem. What if the flash is brand new or has just been erased? The state of flash after being erased is that all bits are set to 1 or 0xFF. If we directly copy this 0xFF data into the struct, the parameter values will be corrupted and could cause system malfunction. To handle this, I implemented a data validation mechanism using a start of frame or SOF and end of frame or EOF. I added 2 special marker bytes at the beginning and end of my struct before saving it to flash. At boot, the microcontroller not only reads the data, but also checks its integrity. If the SOF and EOF values in flash do not match the expected markers, the microcontroller concludes that the flash data is invalid or empty. In this case, the system ignores the flash data and instead uses the default parameter values predefined in the code, ensuring the system operates safely and consistently from the start. Now, let's see how all this theory works in practice. I'll demonstrate that the system is currently running with default values. When I set the set point to 90 degrees, you can see there is a significant overshoot and a long settling time. This happens because the PID gains are still arbitrary. Through the command line interface in this software, I will tune the parameters for position control. The motor's response now becomes much better. Then I save all these parameters and completely power off the supply to simulate a power loss condition. When I turn the system back on, the results are very satisfying. The motor response remains stable and exactly the same as the tuned result before. When I check the PID parameter values through the software, all the values are still intact, safely stored in flash memory. This is exactly what we want. Set it and forget it. We only need to tune once, save it, and the system will always remember the configuration even if the power is turned off. Thank you for watching this episode, and see you in the next one.